Hi everybody. In this lesson I wanted to look at how you use the graph of a relation or a function. And the graph of a relation gives us a picture of it that's very useful for easily determining its domain and range and whether or not it is a function. So to tell whether or not it's a function, we use something called the vertical line test, and that says that a relation is a function if and only if no vertical line will intersect its graph in more than one place. So for example, here is a set of ordered pairs. That's a relation. If I plot those, I will, here's the point 4, 2, 1, 1, 0, 0, 1, negative 1, and 4, negative 2. And if you draw a vertical line, let me get a different color here. If I draw a vertical line right here, you can see that that vertical line is going to intersect that graph in two places. And what that indicates is that this x value of 4 has two y values paired with it. There's a y value of 2 here and a y value of negative 2 here. And see, that corresponds. Here you can see that that's not a function because you have the x value 4 paired with both 2 and negative 2, and in terms of the graph over here, that corresponds to this vertical line intersecting that graph in two places. You can also see the domain. The domain is a set of x values. So if you look along the x-axis, you'll see that there's an x value here, here, and here. Anywhere that there's graph paired with an x value, that x value has to be in the domain. You can see, like right here at negative 2, there's no ordered pair, right? If there was, I'd have a dot there, and then that would have to be in the domain. But the only places that there are ordered pairs is here at 0, 1, and 4. And of course that corresponds with these points, these x values there. Likewise, the range are these guys. I notice that, like negative 4, there's no ordered pair there. There's no ordered pairs until I get up here to y equals negative 2, and then here at negative 1, also at 0, 1, and 2. And these are the only y values that have any graph paired with them. And so that range would be just the set of that has negative 2, negative 1, 0, 1, and 2. Of course, that corresponds to the y values up there. So let's look at another more interesting example here. This is most of our relations or functions that we have in algebra have an infinite number of ordered pairs, and so we can't just list them like I did in that first example. So here's a set of ordered pairs x, y such that I'm going to describe it using this formula such that x minus 1 squared plus y squared equals 1. Well, if I were to find every single ordered pair in the whole wide world that made this true, it would turn out to be the points on this circle. We'll learn more about how to graph relations like that in college algebra. But what I can tell right away is that this is not a function, just at a glance, because right here, or in fact anywhere on that circle, if I try and intersect it with a vertical line, it's going to intersect in 2 points. So what that means is that this ordered pair, or this x value of 1, has both a y value of positive 1 paired with it, and a y value of negative 1 paired with it. By the way, notice that if you come over here and plug in x equals 1, this part would be 0, and you get y squared equals 1, and so both y equals positive 1 and negative 1 make it true. So there are two ordered pairs, so that's not a function. Now you can also look at the domain and see, okay, well obviously negative 1 over here along the x-axis, that's not in the domain because there's no graph there. None of these are until I get right here, and you see that all of the points between 0 and 2 have graph. There's going to be an ordered pair, right? If I have some like over here at maybe a half, right? You can see there's going to be an ordered pair up here that has a half as the x value. So just at a glance, you can see that the domain is going to be the set of x's such that x is between 0 and 2, including, in fact, 0 and 2. And we can write that in interval notation as the interval from 0 to 2 like that. Likewise, the range there's no, down here below -1, there's no graph, but all of these y values here between -1 and 1 are going to have, ordered pairs that have a y value of that's included there in the range. So your range here is going to be the set of y such that y is between -1 and 1. And I could write that in interval notation as the interval from -1 to 1. And again, those square brackets mean that it includes those endpoints. All right. Here's one more example of that. Y equals x squared minus 4. If I graph that, I get this nice parabola, and just at a glance, you can see that anywhere I draw a vertical line, it is going to intersect that graph in just one point, right? Anywhere I put that along here. And so that means that, for example, at this x value, there's only one y value, and that's what it takes to be a function. So yes, that one's a function. I can also look at this, and I understand that this actually has arrows on it. It goes up. And so all of these x's along the x-axis, if I'm over here, if I go up far enough, that's going to hit that. So all of these guys are going to be in the domain. So the domain would be all real numbers, or the interval from -infinity to +infinity. And the range, well, I can see down here that this guy's not going to be in the range, right? -5, there's no ordered pairs, but starting right here at -4, all of those guys are going to be in the range. So the range would be the set of y's such that y is greater than or equal to -4, or I could write that as the interval from -4 to infinity. Okay? Now, let's ask ourselves a couple questions here. What member of the range is paired with 3 in the domain? So if I look here at 3 in the domain right here, 1, 2, 3, it looks like that would be this point here that's like 1, 2, 3, 4. I don't know if it's 3 squared is 9 minus 4. I maybe don't have a high enough on my graph there, but that's going to be about 5. Okay, so what member of the range is paired with 3 in the domain? That's going to be 5, because I plug in x equals 3 and I get out 5, and you can sort of see it, this point up here. This would be the point 3, 5. Another question is, what member or members of the domain are paired with -3 in the range? So this is saying, tell me the x values whose y value is -3. And if I look down here on the y-axis at -3, you see that there's an x value right here that has that y value, and there's another x value over here. There's actually 2 of them, isn't there? So x equals 1 and -1, I'll just abbreviate that, plus or minus 1, both of those have a range value of -3. Now another question is what members of the domain are paired with 0 in the range? And so you see that if the y value is 0, you're right here on the x-axis, and that's going to be 2 and -2. Now those are very special range values. Whenever the range value is 0, we call those the zeros. So the members of the domain that are paired with 0 in the range, we call those zeros the zeros of the function or the relation. And you'll notice that the x-intercepts of a graph always give you those zeros. All right? So very quickly, one more little problem here I'd like to share with you. If we're asked to find the zeros of a function, you can do that one of 2 ways. You can either do it graphically, you could graph this, or you could do it algebraically. So graphically, I look at this and I say, I know that's a line, right? That's like y equals mx plus b. I know the y-intercept's -3. The slope is a half. That's a rise of 1, run of 2, rise of 1, run of 2, and so on. So I can graph that very, very quickly here. Get the right color here. So it looks like that. And you can see once you have the graph that it crosses the x-axis at x equals 6. Okay, so right away I see that x equals 6 is the 0 graphically. Now if I want to do it algebraically, the zeros are where the y value is 0. So I want to set that y value, the function value, equal to 0, and then just find the corresponding x value. So I just solve that equation. I'd bring the 3 over on this side, and then multiply both sides of that equation by 2. And I get on this side x, and on this side I get 6. Same thing as we did there. Okay?